Hello, everyone. My name is Christian Brownlees, and today I'm going to talk about empirical risk minimization for time series, which is joint research with Giorgio and Terrazzas. In this paper, we study time series forecasting from a learning theory perspective, and we establish non-parametric prediction performance guarantees for time series prediction. Now, let me give you a very rough summary of what this paper does. The main result established in this paper implies, for instance, that the Gaussian maximum likelihood estimator of ARMA or GARCH models is consistent for prediction when the data is generated by a class of parameter-driven processes, and in particular when the ARMA or the GARCH are fully misspecified. Let me remark that the main result established in this paper is establishing a general framework that covers different types of forecasting applications that we encounter in time series, and in particular in financial econometrics, and it is derived from primitive assumptions. Let me introduce the framework. We are concerned with out-of-sample, one-step ahead prediction of a time series YT. YT is univariate and is generated by a parameter-driven process. In particular, it could be a linear state space or a stochastic volatility models. YT is predicted using a class of recursive algorithms. This class is called recursive because the forecast produced at time t is a function of the lat forecast in the previous period. The class of algorithms is indexed by theta, which is a vector, and it's called a prediction rule. Important, the relationship between yt and f theta t, it's not specified. For this reason, we call f theta t an algorithm, or you could call it a forecasting procedure if you want. The class of recursive algorithms that we consider would look fairly familiar to you. It includes, as special cases, ARMA and GARCH models. Finally, the loss function, we use a loss function, the Bregman class, to measure prediction accuracy. This is a wide family of loss functions that includes, as special cases, the square loss and the Q-like loss. Okay, so what's the problem of interest? We have some in-sample data, y1 to yt, and we use the in-sample data to choose a prediction rule, which is denoted by theta hat. And then we observe sequentially the out-of-sample data, and we use the prediction rule obtained from the in-sample data for prediction. We choose theta hat by empirical risk minimization. That is, we choose the theta hat that minimizes the in-sample risk when we use the class of algorithms to predict the data generating process. And from a theoretical perspective, what we care about is deriving bounds on the performance of the empirical risk minimizer, where the performance of the empirical risk minimizer is measured by this quantity in this slide. So it's the conditional expectation of the out-of-sample loss given the in-sample data. Main theorem, under assumption in the paper, we have that the empirical risk minimizer satisfies this inequality. Now, what does this mean? This inequality implies that the URM is consistent for prediction. That is, the discrepancy between the performance of the empirical risk minimizer and the best possible performance that you can hope to achieve in the class goes to zero when t is large. What we believe it's maybe interesting about this paper is how this result is obtained. The proof builds upon the literature on linear time series. Turns out that if you want to establish the main theorem, you need to know appropriate moment-independent properties of the joint system given by the data and the algorithm. Problem is, these are difficult to obtain because f theta t, it's an algorithm that depends on the entire past history of the process. Proof strategy consists in embedding yt f theta t in a companion Markov chain. And we establish then properties of the companion Markov chain that implies that yt and f theta t satisfy appropriate moment and dependence assumptions, in particular these alpha mixing. So in a way, the new idea with respect to the classic literature on linear time series model consists in using Markov chain theory to establish moment-independent properties of an algorithm, as opposed to what is typically done, which is using Markov chain theory to establish moment-independent properties of a model. So let me conclude. Empirical risk minimization and learning theory paved the way for the development of new algorithmic forecasting strategy for time series applications, as opposed to model-based forecasting strategies. And importantly, the tools developed in the nonlinear time series literature allow to develop general non-parametric theory to study the properties of these algorithmic strategies from primitive assumption. Thank you.